Great.
Okay, our next speaker is Owen Rehrauer. You know, he's a colleague of mine. This also means we have sometimes a different type of communication. And so when I asked him for his short bio, for his introduction, I only got that Owen has a PhD from Purdue, and he was working there and got this PhD on applying Raman laser to prepare chicken. This is what I have here.
Sure.
No. Owen actually is the president of our US subsidiary, and he started to build it up back in 2020 when we founded it. He leads the team over there, and the years before, he was an independent consultant with exactly one customer, and he helped us quite a lot during COVID and travel bans to keep our US business running and to keep our US customers happy. Indeed, he holds a PhD in physical chemistry from Purdue, and I guess it's not that much about cooking chicken. And I'm really happy to have him as close colleague and friend, and stage is yours.
Awesome. Thanks, Sebastian. Hi. Thanks for having me. I know it's always hard to listen to talks after lunch, so I'm going to try to make this interactive so nobody falls asleep. We'll see if I'm successful in that or not. What I want to talk about today really is a explanation and hopefully give some insight into the strategy that Sentronic is going to be taking with some of its recent releases and some future releases, as well as some of the talks you're going to hear from myself, my colleague Adam Risch, and some of the stuff you'll hear later next year at IFPAC. To set that up, though, I want to just set the stage by talking. Oh, this seems to be going on its own. Set this up by asking the PAT community, how's PAT been doing? It's been about 20 years since the FDA released the PAT initiative, and I think it's worth reflecting on 2 decades of what should be PAT in industry. And I think it's been reasonably successful broadly in pharmaceuticals. You can point to continuous manufacturing filings. We've got 7 now, all of which involve PAT. We can point to the ubiquity of things like Raman or FBRM in biomanufacturing. We can look at softer things, sales of instrument companies. You probably see a lot more folks with Sentronic shirts on here than you did 10 years ago. We can also go to places like AAPS, which are not focused on PAT. We no longer see setup slides for explaining what Raman spectroscopy is, explaining what NIR is. These are kind of normal things people do. I think PAT in general has done very well. When we drill down to specific techniques, though, like NIR, I think there's some differences. So let's talk a bit about NIR. How is NIR done in penetrating into the broader OSD pharmaceutical manufacturing environment? Lots of ways we can talk about this. I'm going to use a tool that Bob Meyer at Merck introduced at the Continuous Manufacturing Forum meeting earlier this year in the States, and that's the Rogers Diffusion of Innovation Curve. I'm not going to over-explain a bell curve to this audience, but the idea is when we talk about this, where in the market do we think we are? Do we think a technology is mostly with new people, innovators, or do we think it's with general adopters? Does everyone use it except for people that are maybe a bit of a Luddite? We can look at things like liquid chromatography. When I was born, that was very much an innovator solution. I think today it's very strange to not see liquid chromatography in a pharmaceutical company. So show of hands, or just call it out. Where do we think the NIR PAT is on this curve? Okay, well, you cheated because I showed you the answer, but I am genuinely asking. I've got an opinion on this, but I might be the odd person out. But in the interest of moving the talk along, I think it's mostly with early adopters. When I look at my customer base in the United States, and maybe things are a bit different in Europe, most of the people I talk to work at large, innovative pharmaceutical companies. I don't talk a lot with smaller pharmaceutical companies. I don't talk a whole lot with generic houses. That's a big chunk of the pharmaceutical OSD manufacturing market. And I think it's worth asking why. So we've had a lot of conversations with some of those companies. We've had a lot of conversations with equipment suppliers like Gerica, Gaia, et cetera, on why they think it is that there's some challenges getting that segment of the market to adopt PAT. There's a few reasons people may or may not adopt new technology. This seems to be going on its own, so it'll be interesting. What drives adoption of new technology? I'm not going to read off the slide to you all, but Is it a matter of people don't see the value in it, it's not a good fit for them, or is it a matter that there's barriers to adoption? And you talk to people, they understand the reason people want to use PAT. They see value in the PAT. It's not too expensive, people can afford it. The challenge is in the expertise needed to use it. So they don't have a PAT person. We get told that there's concerns about hardness for an industrial environment. So if I bring this in, am I going to have to babysit the PAT to make sure it's used? And we get a lot of concerns about regulatory impact. If you don't have a PAT person, you don't have the expertise in a company, how do you file? That's not common knowledge. You have to bring on consultants, and that can create a barrier, both financial and just management within a company to get this technology in. So as an instrument provider, I think it behooves us to try to address some of those concerns. Obviously, our existing customers may have different, more specific concerns. They're expert users. They do have the expertise. We are absolutely still going to continue to address those concerns, but I don't think there's anybody in the room who's going to argue with me, everything else being equal, if we took our products and made them easier to use, I don't think anyone's going to object to that. So that's really our goal within Sentronic. We're going to take technology and try to give you some techniques that might make NIR PAT a bit easier to adopt. Let's start with the technology. I'm using we very loosely here. This was all developed before I joined Sentronic. Uwe, Sebastian, the team here, as well as with some industry collaborators, Phil, Steve, Martin. Very, very useful in bringing internal standards into our instruments. I'm not going to over-explain this because we've talked about these a million times. We have internal intensity standards as well as internal wavelength standards. The intensity standards offer a lot for novice users. If we can avoid bringing fundamental standards to the floor, that's a big win, just from a day-to-day operation perspective. In terms of avoiding damage to the white standards, these can be a bit expensive. There's a big win there. I've spent, and I think some people in the room have spent weeks trying to track down why spectra look strange and tracing it back to a dirty white standard. If we can avoid that problem at a fundamental level, let's do that. The wavelength standards, we've seen some other talks on these here. One of the big advantages of these, beyond just locking in a consistent x-axis, so we don't have to worry about drift as a function of time, is we've enabled or reduced, almost eliminated, the need for cal transfer from our devices. Pfizer-Groton has a very nice paper demonstrating this. I can't say we completely eliminated it. There may be systems where this is not the case. One of the side effects of the internal wavelength standard, though, is that we've normalized our x-axis across our fleet of instruments, making it much easier to build a method on system 1 and transfer it to system 2. We've also implemented outlier rejection, particularly in cases when we have routine poor sample presentation in front of our probe. That could be caused by, for example, fingers in the feed frame of a tablet press, fingers in the back of a spider wheel from Expo Process Analytics. You can see here an example of spectrum measured with, and without outlier rejection. You can see the great improvement in spectral quality there. Obviously, there's other ways to approach this problem. You can do this in post-processing, but for novice users, that's a big ask. That's a big challenge for them. By solving this at the engineering level, we believe that this really helps make PAT a bit easier to use. You can see our new system coming out next year, the SentroCOMPACT over there. Folks who were here yesterday got to see this live. We've tried to simplify our systems a lot. It sounds silly, it sounds trivial. It's really not in day-to-day practice. We've removed the need for a fiber optic cable on the production floor. A number of times we have, I don't know why this is jumping ahead on me, so apologies for the back forth. We've had issues with cables getting run over, cables getting loose and disconnected, and poor spectral quality as a result of that, failing SST test groups. Just eliminating that from an engineering level, we see a big, big advantage of. No longer having a probe and a base station, just having everything all in one box. It sounds simple, but from a reliability, from an approachability perspective, we think this is a big win. Software is obviously a big piece of this too. I think Dirk did an excellent job yesterday of introducing and talking a lot about the concepts we have here, but we are trying to make the software easy to use here. For some users, they're still going to want to use our software. Our bin blending customers tend to be in that case, early development tends to be in that case, and we want to continue to support SentroSuite for those users, making it still easier to use. Dirk's doing some really good work there. Our CM customers, though, we want to try to get SentroSuite a bit out of the way. They tend to want to, after the initial setup, just run in SentroPAT, SentroQ, ProAsix, etc. let's give them an engineering window so we can do things like run validation tests, et cetera, and then let that software drive everything else. In terms of regulations, though, what's the regulatory impact of these changes? The internal standards probably the only bit here that really has a regulatory impact. The recent update to the USP chapter, 1856, has been very, very helpful in that it explicitly spells out you can use internal standards for process instruments. That's been a great help. We haven't got a whole lot of questions from customers on on-site review, so this seems to be something that's been well accepted. It doesn't add any additional risk to the use of the process. That having been said, the technology end's only a piece of the puzzle. And I think at the end of the day, hardening these is helpful, but the big challenge is technical expertise. It's great having spectra, but it's really challenging to turn this mess into something that a formulator can use, a control chart. So how do we do that? We use multivariate data analysis. That's a specialized skill set that not everyone has. I think that's a big challenge for usability for us. So what can we do to improve it? We've got a family of methods that have been successful for getting information out of NIR spectra. Sebastian Savinsky, who introduced me, doesn't have a background in MVDA, but he's helped countless numbers of customers successfully implement things like moving block standard deviation analysis. Set that up very easily, and you get a blend curve out of a BIM blending system. That's great, but much like Manel described, it's great to show that, hey, I can get you a blend curve, but formulators tend to want to get information about potency. Maybe they've seen a talk from any number of us in the room on, hey, look at this great thing, I can predict what the HPLC says, and they often want that. That's a little bit harder to do. If we try to introduce PLS, there's a lot more jargon we need to do. We need to introduce a reference method. It can be a bit hard. So how do we get qualitative information using something as simple as a moving block standard deviation so that it doesn't have a high calibration burden? I think one of the approaches we can take is pure component methods, things like classical least squares, IoT. So I want to make the case for those. I think there's been some recent innovations, and we hope to help contribute there a bit as well. Before I jump to that, though, I want to talk about what success might look like here. Talking to the many formulators I know and talk to routinely, what would a method that was suitable for them look like? It needs to be easy to understand. It needs to require minimal training, and I mean that in both the sense of training from like a calibration perspective and training from a user use perspective. And it should be in something that either is in our software so they can use it immediately, or they can do in Excel. That tends to be the ask, and they'd love it if it's never can be updated. I don't know if that's realistic, but hey, it's the ideal. For the non-chemometricians in the room, I just want to kind of explain the differences when I talk about a pure component method versus an empirical method. That's jargon that not everyone knows, so let's talk about what that means. A pure component method is a method where you measure the pure chemicals in a mixture. So let's measure pure API, pure excipient, and then use that information to derive some quantitative information from the system. So we don't have a calibration set like we would in a PCA or PLS analysis. These can be very powerful. The challenges for these tend to be when we have deviations from Beer's law. So when our spectral change is not linear in response to a concentration of our analyte change. Contrast that with something like PLS, which we all know and love. It requires a calibration set that can be a bit burdensome to get, but the strength of these methods is they can better handle nonlinearities in concentration response with spectral response. Going through the math, I promise you, if the equations are uncomfortable for you, we're not going to dwell on them too long. But just explaining what the difference between two methods I'm going to talk about today are. Classical least squares is just linear algebra. We assume that there's a mixture spectrum that is literally just the linear combination of pure components based upon their weight. We can estimate if we have a mixture spectrum we measured, we know the spectrum of all the chemicals that went into it, what the concentrations are in an unbiased way. This is really easy to do. It's very, very fast for a computer to calculate. The challenge is it can come up with an answer that is mathematically correct but physically impossible. So you can have negative concentrations. You can have 110% concentration. That can be a bit strange for people to see and a bit of a strange thing. In contrast to that, I'm going to talk a bit more about IoT, which is an algorithm that does something very similar. We're assuming linear mixtures, but rather than using least squares math to solve it, we use an optimization to solve it. So we might use something like a genetic algorithm to try to optimize the concentrations. What's nice about the optimization is we can put constraints on it. So we can say, hey, you can't have a negative, negative concentration. All the concentrations have to add up to 1, which would make sense. You know, if we're going to have 87% and 13%, that should add up to 100%. If we have 87% and 50%, something's a bit strange. So it makes the results a little bit more physically interpretable. The downside is it can take a little bit longer to run. This tends to be, you know, microseconds for CLS versus a few milliseconds for IoT. On the time scale we're talking about typically, that's not too burdensome, but I do want to call that out as a downside of IoT relative to CLS, but for our purpose, we still seem to be fit for purpose. One note, I was challenged by a former coworker on, you know, why am I talking about this? Isn't this just a bit of a trend? So I'm going to show something that's not NIR here. Sorry, Sebastian. You know, it's a good challenge. I do want to talk about it a bit. I've had a lot of success in my career using pure component methods. When I worked for Vertex, obviously I used them there, but I can't show data from that company. I've worked with other clients on this. I can't show their data. What I can show is what I did in graduate school. So this is Raman spectroscopy as opposed to NIR. This is point scanning video. We used a pure component method, all Raman spectroscopy, pure components, no spectral preprocessing, to measure point by point over, these are crystals of caffeine and acetaminophen. Each point was measured in 10 microseconds. I know this isn't a Raman conference, but for Raman, that's very, very fast. These methods can be very powerful when they're used in the appropriate way, but we have to use them in the appropriate way. And I think there are some appropriate ways to use these sorts of mathematical techniques to be successful in NIR analysis of pharmaceuticals. So let's talk about a case study and do just that. So this is an abbreviated version of a talk that Adam prepared for SciEx. So thank you, Adam, for the hard work on this. This is a comparison of PLS and IoT for two very simple caffeine, which is just a dummy for API, and MCC mixtures. We made a 40% potency caffeine and a 10% potency caffeine blend, 70 to 130 with a calibration set for PLS, a test set for IoT. Built our models up. We collected pure component spectra using the SentroPAT DA, made these blends, mixed them on the central blender, got everything done with about 30 to 50 grams of material. So nice and lean, material sparing stuff there, but let's compare the results. Let's look at how well PLS does, let's look at how IoT does, and compare in a rigorous way how much material we had to use for each of these methods. Let's talk about the results first, because I think that's what everyone wants to get to. You can see calibration and test set for PLS. You can see just showing the test set for IoT. Look really similar. We go to the figures of merit. RMSEP here, R squared, look very, very similar. I've put up here the pre-processing just for people to take a look at. I should note too, Adam and I are happy to make this data available. If you want to play with it, double check our work, make sure we're not doing anything funny. But we were really encouraged by this. We seem to get very, very similar results using the two methods. So let's compare the material time and the financial cost of the material altogether for IoT and PLS. A lot of colors going on here. One thing you may notice is that the low dose has more test samples than the high dose. I ran out of caffeine in my house, so sorry for that. Not the most rigorous thing there, but if you can forgive that, we can compare the time required to collect the samples. You can see that, unsurprisingly, the one with more samples took me more time to collect. We can compare the material required. Unsurprisingly, the method that took more samples took more material. We use some example numbers here. Obviously, caffeine, MCC are both very cheap. There's a reference here from Matsunumi et al., which is comparing batch versus continuous budgetary concerns. Really, really good reference. I'd recommend people check it out. They gave just as a typical API cost of $100 per kilogram. Obviously, in early development, that could be orders of magnitude higher, but considering generics as well, we're just going to take that as a typical. I'm not going to read off the slide for the labor cost, excipient costs, but here's the estimated costs. We integrate those together, high level. IoT saves us somewhere between a factor of 2 and a factor of 3 relative to PLS for similar results. I want to emphasize again, for similar results. It's not getting you better results. I do not want people to come away with that conclusion. But to get to the same place, we do that for a factor of 2 or 3 cheaper, that's a big win. And that's not just from this one experiment. We see lots of examples of comparability with PLS in the literature. So this isn't a one-off. This does seem to be something that is fairly general. at least for low-dimensional problems. What I mean by that is if our blends aren't too complicated, we don't have 9, 10 components in the blend that we're trying to predict, we seem to do well. At a very, very high level, I think it's also worth talking about where these tools might be the right tool to pull out of the toolbox. I think if we're talking about what I'll call guardrail PAT, these can be very, very useful. So if we're looking for PAT as a backstop to an RTD method or a DEM method, if we're looking for PAT just to confirm that the assumptions in our manufacturing are right, that we're moving in the right direction, these can be great fit-for-purpose models. If we have a high criticality PAT deployment, if you're doing things like trying to do RT-RT, I don't know that this necessarily is going to be the best tool in our toolbox to pull out, mostly for regulatory reasons. I'll explain that in a minute. But also, I think we should be honest with ourselves about where we are in the development of these tools. I mean, Adam was the one who developed an equivalent to Hotelling's t-squared for these tools, and that paper was published last year. It's still a very novel technique. I don't know if we have enough confirmation of this yet to be confident to go to a regulator off a single paper. I think it's going to take time. It's going to take more testing for these to get ready to be there for that level of scrutiny, but I think we're moving in that direction. And I think we should consider promoting these tools, particularly for people that are evaluating PAT feasibility, taking their first steps into the pond. Obviously, though, okay, great, I'm talking about IoT. How do I do IoT? And until very recently, the answer has been, well, here's MATLAB code, here's some Python code. That can be a bit intimidating for new users. It can be a bit intimidating for a lot of users. So to bridge that gap, we're putting it into our software. I know some other folks have committed. Brad, I don't know where you are. Brad, there you go, is also committed to putting it in his software. So TBD on SentroSuite, but I do think you're going to see this come down the pipe a bit more for lots of people. Regulatory concerns. I do want to highlight that for things like IoT, there is no FDA or EMA guidance on how to deploy these methods. I think there's lots of analogies we can draw to how PLS methods are drawn. I think we can point to things like the metrics and ICH guidances and still meet those metrics, but it's an emerging technique and we should be honest with ourselves about that. I think there's an opportunity to educate regulators, but I think that is still going to take some time. So I have been talking very, very fast. Sebastian's probably going to yell at me in a minute. We're already at the end of their slides. Obviously, we talked about the motivation for this. I want to highlight here, I've shown some AI images here. I think we're really at a crossroads. I think lots of people have identified the problem we're talking about, the difficulty and complexity of deploying PAT. I think there's two solutions that are really being considered right now. One is a solution I just talked about. Let's make PAT simple. Let's make it easy to use. Let's make it understandable so non-experts can use it and be successful. The other option is let's just take AI, let's let AI do all the magic, and hopefully that gets us to the right result. I'm a little bit pessimistic on the success of that, but I know it's a popular solution, particularly for people in the C-suite, as we've heard today from some people, but that's not the only time I've heard that. So I think we have an opportunity to help maybe steer things in a way that's a little bit more scientifically defendable, but I do want to call out it's in contrast with, I think, some general industry trends. So I'm going to throw that out there for food to thought. We have a ton of time for questions, so
it's not a ton.
Okay.
Just to be clear.
Okay.
Thank you, Owen. And another comment, I'm not sad that you use Raman data for this presentation. It is not an NIR conference. It is not a user group meeting. It's on PET. And as far as I heard, rumor-wise, Raman is used there as well. So, sorry, Sasha. Yeah, questions to Owen. Yeah, usually the chair should jump in now, but trouble is I reviewed this presentation a couple of times and got all questions answered. So, no question. Manuel. Thank you.
Thanks for the good talk. I have a question about the IoT. Is there a way you can, 1K, start using IoT and then updating the model based on new data, and then so you can update the model without the so-called update, because you said, well, that people don't want to have methods that have to be updated, but is there a way you can combine both approaches a bit?
Yeah, so there's lots of ways one could update an IoT method. I think it comes down to why the method needs to be updated, I think that's always the question. Even with PLS, oh, okay, we have to update this. Why did the model not predict correctly? One example could be if we have a change in, let's say, raw materials. We move from vendor 1 for lactose to vendor 2. That lactose might look different. If we just update what the pure component spectra looks like, make predictions, I think that's a very technically justifiable and easy way to make the update. Obviously, in a GMP environment, there's all sorts of validations. But in general, there is that. The other thing could be we could see differences in physical properties. Maybe the pre-processing we selected based upon what we knew about the process variants get less in one place. As we get more understanding of the true process variants, true changes in physical differences, we don't need to update our pre-processing to better make our systems robust to those physical changes. So I think you could do pre-processing, you could change the pure components from kind of two ways you can go with that from a technical perspective. I think both are technically justifiable, but which way you go, I think depends on what the motivation is for the update.
Just to build on that a little bit, I've seen one example where the offset in prediction has itself been used as a determination of the stability of the process. so actually, physically trending how wrong it is actually giving useful information on the process change.
Absolutely. Yeah, no, good point.
Okay, while coming back from thanks again, Owen. Great talk.